Greetings. I'm Xavier Rico, a fourth year cadet at the United States Air Force Academy. This summer, I had the privilege of conducting research at Carnegie Mellon University's Biorobotics Lab through the Robotics Institute Summer Scholars Program. My research focused on disturbance-observer-based station-keeping control for the Hardened underwater modular robot Snake. Aging underwater infrastructure requires frequent inspection and preventative maintenance. Performing this maintenance before a failure occurs can reduce costs compared with reactive maintenance. However, many underwater structures contain confined, hazardous, or difficult to access spaces. Underwater robots, specifically underwater robot snakes such as the HUMRS, are designed to operate in these environments. Their articulated bodies and multiple internal degrees of freedom allow them to maneuver through spaces that conventional underwater vehicles cannot. However, inspection and maintenance tasks often require the robot's head to maintain a desired position and orientation. This is known as station keeping. For HUMRS, station keeping is difficult because of the unknown hydrodynamics and external disturbances, as well as the HUMRS' under-actuated design. The objective of this research is to design a controller to maintain the HUMRS' head at a desired position and axis while rejecting non-linear disturbances. The controller minimizes two errors: the position error of the head, E, and the tilt error, theta tilt, between the desired axis and the head's longitudinal axis. Rather than using the full Lie algebraic error, the controller intentionally disregards rotation about the robot's longitudinal axis. This is because HUMRS is underactuated in roll and cannot directly control that degree of freedom. By controlling the head position and pointing direction instead, the controller focuses only on the components of the pose that the HUMRS can meaningfully regulate. The control system consists of two main components. The first, the propellers use PD control along with feed-forward compensation for gravity and buoyancy. Second, the joints also use PD control with compensation for gravity and buoyancy. To evaluate the station-keeping controller, the HUMRS was subjected to four types of external disturbances: a sinusoidal disturbance, a multi-sign disturbance, a Gaussian disturbance, and a step disturbance. The baseline PD controller does not explicitly estimate these disturbances. Therefore, it cannot truly compensate for them, leading to position error and inability to maintain its station-keeping objective. To improve performance, I implemented a disturbance observer, shifting towards disturbance-observer-based control. The disturbance observer compares the motion of the HUMRS with the motion predicted by a nominal dynamics model. Using the measured velocity and an acceleration estimate obtained through finite differencing, the recursive Newton-Euler algorithm, an inverse dynamics algorithm, calculates the generalized force required to produce the observed motion. This is tau d hat, which is a measurement of the external disturbance tau d. We can now examine how the disturbance observer affects station-keeping performance. First, we will start off with the step disturbance. Under step disturbance, PD controllers are unable to eliminate the steady state error and the robot drifts far from the desired position. However, once the disturbance observer compensation is introduced, the error decreases substantially. Observing Gaussian disturbance, a similar pattern occurs. With only PD control, the robot experiences large and irregular position errors that it is unable to correct. Once the disturbance observer is implemented, station keeping is greatly improved, although the remaining error is larger than for some other disturbance profiles, as can be seen. Regarding the sinusoidal disturbance, the uncompensated robot repeatedly moves away from the desired position and oscillates. When the disturbance observer is implemented, the position error is significantly reduced, but these oscillations can still be observed. Finally, we examine the multi-sign disturbance. The PD control, again, deviates considerably from the desired pose. But after the disturbance observer compensation is introduced, the robot remains much closer to its commanded position. Next, we will look at the results. For a quantitative evaluation, each disturbance type was tested at 20 disturbance levels ranging from 10 to 200 newtons in 10 newton increments. The sinusoidal disturbance was used as the reference. For each sinusoidal peak amplitude, its root mean square force was calculated. The step, Gaussian, and multi-sign disturbances were then scaled to match that RMS force, allowing their effects to be compared more fairly. Without the disturbance observer enabled, the RMS position error decreased dramatically for all 4 disturbance types. The Gaussian disturbance produced the largest remaining error, while the multi-sign disturbance unexpectedly resulted in slightly lower error than the single frequency sinusoidal disturbance. These results are limited by several key assumptions. First, the simulation uses noise-free estimates and assumes that the nominal model accurately represents the robot, even though the complete system identification of the HUMRS has not yet been performed. This evaluation also assumes ideal and unconstrained thrusters without command deadband, actuator dynamics, or maximum thrust limits. These assumptions isolate the performance of the control architecture, but they do not fully represent the robot. Therefore, the results shown here demonstrate that disturbance observer compensation can substantially improve HUMRS station keeping under time-varying external disturbances in simulation. However, they should not yet be interpreted as the disturbance rejection limits of the current hardware on the HUMRS. Thus, future work should evaluate additional joint configurations, robot orientations, measurement noise, model uncertainty, and realistic actuator constraints. Most importantly, the controller and disturbance observer should be implemented on the HUMRS hardware for external validation. This completes my presentation. First, I would like to thank Professor Howie Choset and Dr. Jinwoo Choi of the Biorobotics Lab for their guidance and support. I would also like to thank Dr. John Dolan, Rachel Burson, and the Robotics Institute Summer Scholars Program for making this opportunity possible. Lastly, I would like to thank the United States Air Force Academy's Department of Mechanical Engineering for supporting and funding my participation. Thank you for listening.